There we go. Hello. Hope everyone's doing alright. Welcome back to Chem 161. We'll wind this down here. We got some stuff coming up next week that is due. So, you just finished the quiz, or not finished the quiz, you just finished the chapter from Hell, chapter 3. And, oh my goodness, my cat is already meowing at me. 3 seconds into lecture, Maya, my goodness. Now you take a quiz on chapter 3, and it's due next Tuesday, the 1st of June. Lab worksheet number 4 is also due that day. I do want to talk really briefly about lab worksheet number 4 before we do much of anything. So hold on just a second. So if we go to the Canvas page and you go to the Modules tab, hopefully you've been doing this all along and noticed that, like, oh, there are videos for these labs. I should be watching them. And that's especially important for here because this link that I have, which is going to link you to YouTube, there is a emission spectra video, which is part of the lab. But I also have a video that I made last quarter when I taught Chem 161. We had separate days for lab stuff, so I would do lab and then answer questions that students had, and nobody ever came to them. So I gave this lecture back then. If I had those days this quarter, I would do it now. I was going to make a video with a lot of this content in it just separately, but I really don't have time to sit down and create a new video from scratch. And that would take, like, that's a 10-hour project. And, like, I could get it out this weekend, and yeah, like, you need it sooner than that. So click on this link and you can see the discussion of how to do lab number 4. There is a lot. As you can see, it's 90 minutes long. I'm going to just leave that for you to look at, and I will answer questions as they come up. I need just a second here because my cat will not stop. There we go. She thinks she's clever, hiding just around the corner and meowing at me just to annoy me. All right. So please watch lab lecture number 4 on that link that is in the modules tab. Please do ask me questions and then use the Discord, because the entire lab for part A is just program Excel and calculate the energy for all the possible transitions in hydrogen. From n equals 1 to n equals 10, and that's like hundreds of transitions. If you know what you're doing, you can do the lab in 10 minutes. Most people don't know how to program formulas into Excel, though. And by Excel, I mean Google Sheets. I'm saying Excel because we would be using Excel in the laboratory. But yeah, part B is pretty self-explanatory once you've watched the video. It's just, what do orbitals look like when we put the atoms of their of specific types through a detector called a photo emission spectroscopy. God, I can't even think now. My cat has me all scatterbrained because I just keep hearing her. All right, let me take a drink of water. We'll just focus. I have a real hard time focusing with outside distractions, so I apologize. So, a photo emission spectroscopy experiment is what we are doing in part B of the experiment for lab number 4. And the documentation that I provided and the video will explain that. So please review those on your own time when you can. And again, do ask questions. All right, we left off on Tuesday. Oops, not doing that. Looking at this chart here, where we talked about bond types and the difference in electronegativity. Now, the way that this works is that if I go back to the chart that has electronegativity on it, and I just pick 2 atoms to put in a bond. So let's suppose I had like a CO bond. Those are common enough, right? What I would do is I would check the electronegativities, and I would compute delta En. The difference in electronegativity is always a positive number. You just subtract the smaller one from the bigger one. So for the CO bond, the delta En would be 1.0. Now, based on the number that we get, we then apply it to this chart here. And so for CO would be considered to be polar covalent. Because it's 1.0, that falls between 0.4 and 1.8. Now, I'm actually going to change these numbers for you, because I don't agree with what these numbers are. And I'm making a very important change there, and I would recommend that you do this too, because less than 0.4 is just wrong for one very, very specific reason. And that reason is, if we go back here, oops, sorry, there's text everywhere. And instead of doing CO, we write CH. When I do delta En for this specific bond, I get this. It turns out that CH bonds are, if not one of the most common bonds in the universe, they are the most common bond in the universe. Because carbon and hydrogen love each other. They form bonds all the time. And one of the very, very, very first things that you learn in organic chemistry is that organic compounds made of C and H, hydrocarbons that is, are nonpolar. Well, then this textbook comes along and says, oh, 0.4 polar covalent. Nope, we are not doing that. We're putting you straight into this category where you belong. So I have to edit that number. Otherwise, Samita will murder me. She'll be like, why are you teaching them that CH is polar? I'll be like, I'm not, it's the textbook. Stop hitting me. Samita would never do that. She would be upset if you told her CH was polar, though. She'd be really upset. So do note that modification to the table from the textbook is very important to be made. I will be testing you on this modification and not the 0.4 version. If you put CH as polar on my quiz, I will mark it wrong. So just be mindful of that. Now, what do these terms mean, other than just like shoving a number into a category? Pure covalent means that for our bond, the electron density is completely covalent. It's essentially equal across the bond. There's no noticeable or notable displacement of electron density towards either atom in the bond. So in a CH bond, the electron density is more or less right in the middle. For a polar covalent bond, the electron density is shoved closer to one side than the other. For instance, in the HCl example, the electron density was close to the Cl for the majority of the time. So on average, Cl had more access to the electrons. And we made the analogy of like if you have like a Nintendo Switch that you share with a sibling and they get to play it too, but it stays in your room. That would be an example of uneven sharing. Whereas something that is evenly shared, it would be you both have equal access to it at all times. Finally, ionic is where the electrons are shifted so far over to one side that they are essentially transferred. If you push them too far across the bond, then they just end up being attached to the atom that they are being shoved towards. So if I put sodium and chlorine, sodium's not going to pull at all on those electrons. Chlorine just goes yoink and takes them. And they're both happier that way. So we can categorize any bond using this. You just have to have a structure of it handy to do that. Okay, and so again, I need to change these numbers on this slide. So less than 0.5 and 1.8. Now, according to these numbers, it is possible for you to get combinations of elements that would result in a number less than 1.8 and contain a metal. So for example, if we went over here and I wanted to make a bond between gold and oxygen, and you'll notice that there's no way that that's going to be a difference of 1.8. And you can totally make a gold-oxygen bond. What type of bond will it be? Well, according to this table, I hit 1.1. That's going to be polar covalent, which seems weird because we've been telling you all this time metals and nonmetals form ionic bonds, right? And so this is where the lines sort of start to blur. Like, what actually happens? Turns out you can totally form covalent bonds with metals, all that you want. It's just that you need very specific ligands to do it. Ligands being like molecules instead, like a water would be a ligand as opposed to just an oxygen ion. So keep in mind that this numbering scheme that we have here is sort of just a model. And that you don't want to apply it to absolutely everything without any consideration. So it might be that we can make gold 3 oxide or something like that, or gold 1 oxide, or whatever the oxidation state of gold is, as an ionic compound. But there could also be gold compounds out there that do covalently bond with oxygen. So if you land kind of in the gray area, it's very likely that both possibilities exist. So don't be surprised, I guess, if you see some of those, not in this class, but like outside, like, the chart lied to me. No, the chart's a model. So for our purposes, I'm going to have you classify stuff according to this chart, and I'm not going to give you the weird exceptions that land in the middle that would be weird or surprising. We might see one or two of them inadvertently. I know I have some problems with like tin that is covalently bonded because it totally does that. All right. How do we how do we display electronegativity on a structure? We have two ways to do that. So the first way is to use these symbols here. So if you've taken calculus and you've seen like the Greek symbol delta in lowercase, you know that that means partial, right? The lowercase delta is used for partial derivatives. Now, we're not going to do calculus in this class, obviously, but there is precedent that delta is used to indicate part of something. Now, because my HF molecule is not ionic, so it's not got this going on for it. Oops. It doesn't have a positive and a negative completely split. It's not ionic. Instead, the electron density in this bond is shoved to the fluorine side in such a way that there is more electron density near fluorine than there is on hydrogen, but not enough to be equivalent to one electron. So we write the partial symbol here to represent part of an electron has been moved. Now, obviously, you can't dice up electrons into tiny pieces and say, okay, here, have half an electron. But if the electrons are moving really quickly, and you take a snapshot at any instant, most of the time they're going to be on the right, and the rest of the time they'll be on the left. Not as often, but most of the time. And these symbols just represent that statistical average. The end result is that we take the delta plus symbol and you put it on the element that's less electronegative. In this case, that's hydrogen. The delta minus symbol goes next to the more electronegative atom, and that's fluorine. And you do that for along a bond, or you can do that for an entire molecule. So for example, with water looks like this. If I was to draw delta plus and delta minus, the top side where the oxygen is the negative side, and the bottom side where the hydrogens are is the positive side. And we'll demonstrate why that is in more detail later. But for now, just keep in mind that you can use this for an entire molecule. And in fact, that's the most common way to do this. The second method is most common for bonds, and that is to draw an arrow along the bond in the direction of the more electronegative atom. And so fluorine is more electronegative, so we just point an arrow at it, and then we put a little plus on the other end to show that that's the positive side. We're going to use that technique in a little bit. In this chapter, like probably not today. But we're going to use this to describe the polarity of a molecule overall, as opposed to just the polarity of a single bond. All right, so we'll come back to this later on. All right, so what I want you to do is using the electronegativity chart, which you can go back to in the video, but what I'll do is I'll put it on the screen really quickly. Let me clear all this shit off the screen here for you. So you can pause the video here if you need to. Okay, and it's gone. Oops. I want you to categorize each of these bonds as either pure covalent, polar covalent, or ionic. Assume that the little dash that I have is whatever bond forms between those two. So it might be an ionic bond, it might be a covalent bond. All right. I'll see you in a bit. We'll go over the answers in like 2 minutes. One more minute. All right, let's go over the answers here. So for sodium and chlorine, I actually have to go back and look at sodium and chlorine. I know chlorine is 3.0. Sodium is 0.9. Okay. So chlorine is 3.0. Sodium is 0.9. I was writing the answer instead of the number. So I get 2.1, which is very, very, very large. So that's ionic. Now, if we were going to draw symbols for this, you might think, oh, okay, well, I'll just do this for it. But remember that that symbol is synonymous with this symbol. And is this what we observe for sodium and chloride? No, it's totally not what we observe. We observe this, right? Boop, boop. If they're ionic, they transfer whole charges. So we should write the whole charges on that molecule, or formula unit in this case. Oh, is part of the chat not captured on the screen? My window might be too wide. Hold on. There we go. Now, for bromine and iodine, so bromine is... That's 2.5. I was looking at the chat here. Let's go back and look at that. Bromine is 2.8, and iodine is 2.5. So there's a very small electronegativity difference between bromine and iodine. And it's so small that we consider that there is essentially no displacement of electrons between them. So if we were going to draw the bond, we would just draw that and it'd be done. Don't put any sort of mark on it at all because it's pure covalent. Now Bn, N is 3.0, B is what, 2.1? 2.0? I'm going to go with what you have here. So because it's greater than 0.5, but it's less than 1.8, we're polar covalent. That means that the electrons in the bond are shifted towards the more electronegative element. So I would draw this. I could also draw that and that. All right. Let me know if you have any questions. All right. So there's our solutions. All right. Now, for these, what I want you to do is just draw the notations. So, for the ones that need a notation, use either the delta or arrow notation on them. Now, obviously the first one, they're the same thing. You're not going to draw anything, so this one's done. Now, if you don't use arrow notation on it because it's ionic, use pluses and minuses. Okay? So write out the correct notations on your paper, and we'll go over the answers in about two minutes. All right, let's go over the answers. So I have the electronegativity over here on a different page. So I'm just going to refer to them here. So HCl is polar covalent. So the notation we would use would be an arrow notation, or delta plus on the H side and delta minus on the Cl side. For lithium and chlorine, That's ionic, so we would do this. Oops. There we go. 2.1. OH is polar covalent, so along this bond I would be like that, or delta plus and delta minus. There you go. And then HH over here, the difference is 0, so it's just pure covalent. All right. Any questions, let me know. That's how we indicate bonds. Now, in some types of molecules, for instance, polyatomic ions, this is very common. You can have both covalent and ionic bonds at once. So, for instance, if I have ammonium chloride here, in ammonium chloride, I have covalent bonds between the nitrogen and the hydrogen. So all of these lines coming out of them are covalent bonds, but the whole thing is ionic because the whole thing has an overall plus charge, and that interacts with Cl, which has an ionic bond. So it's possible to have a weird edge case where bond types aren't exclusive within a molecule. And this is super common in polyatomic ions because polyatomic ions have to form ionic bonds because they're ions, right? However, in order to be polyatomic ions, they have to have covalent bonds holding them all together. Otherwise, it wouldn't be a polyatomic ion. It would just be an ionic compound. So, if you're asked, like, what types of bonds are present in this molecule, be careful if you're dealing with a polyatomic ion, then you have both covalent bonds and ionic bonds present. All right. We're going to consider that in a little bit more detail later on when we start doing Lewis structures. But for now, we have to do everyone's favorite part of the class, naming everything. We're going to do that today. That's probably what we're going to do for the rest of the day. If we can get to Lewis symbols, that'd be great. If you took 140, you probably spent a day on naming. We're going to spend half a day on naming. So we're going to go through this quickly because this should be review. How do you name stuff? The way that we name compounds in Chem 161 and in just general chemistry is by using the rules of chemical nomenclature. Nomenclature sets out some rules for us that will help us name these categories of compounds in this class. So we've got ionic compounds, which we're going to split into either binary or polyatomic. We've got covalent compounds. And then we've got acids. You're going to see a lot of acids in chemistry, so we're going to try and name them here, even though we haven't talked about acids all that much yet. All right. So we're going to start with naming ionic compounds. You're going to want a periodic table handy to name all of these things. So if you don't have P-table open, go ahead and do that now. The way that I do naming is that I provide you with a template. And what you're going to do is you're going to drop the name of the thing that you're working with in the box. And then you'll put the boxes together, and that's the name of it. The plus symbol indicates that there is a space between the first word and the second word or words. Now, naming the metal is easy. You have a periodic table, you just look at it, right? Now, there are some exceptions to this. And it turns out actually most of the atoms on the periodic table are the exceptions, which make it a little bit more cumbersome to deal with. Now, If the metal that you are working with is in these groups, group 1A, group 2A, or the element is aluminum, all you write on your name for your metal is just the name of the element itself. These metals have fixed charges, and these are the ones that I expect you to know. I don't remember if I have like the little staircase thing. Hold on, let me see. I don't. Okay. There is a slide somewhere in there that has like a staircase that talks about these elements. So aluminum, gallium, zinc, cadmium, and silver. And it just goes like this or something like that. And it says, hey, these are all fixed too. The only one I care about is aluminum of that list. You have enough shit to commit to memory. You don't have to memorize these two. So I'm going to treat aluminum as a fixed charge, and I'm going to treat the rest of them as either fixed or variable, up to however you just want to do it. The quiz should be programmed so that it will accept either answer for silver, cadmium, zinc, or gallium. Now, the reason that we need to make a distinction between fixed and variable charges is because the naming scheme for them is different. So, if you have any other element that is not group 1A, 2A, or aluminum, you need to indicate its charge as a Roman numeral. So, for instance, if I was writing out some element names here, so here are just some random elements. Any of them that fall into group 1A, 2A, or aluminum are fine as they are. If you wrote this, Canvas will mark it wrong, so don't do that. Now, for other elements that have variable charges, we need to indicate the charge in parentheses, whatever it is. Notice that there is no space between the name and the parentheses. And that the Roman numerals are capitalized. The other thing to note is that elements are not proper nouns. So you don't capitalize them. Why do I make a big deal out of that? Because Canvas will accept this as correct. It will mark this wrong. Okay? And if you tell me, hey, I accidentally capitalized the first letter of everything, can I get credit? No, you don't get credit because we had this discussion right here. Okay? So be very careful about spelling because Canvas is going to look at your answer and it's going to compare it to what I have typed in. And if it doesn't match exactly, it's wrong. So be careful, okay? Don't capitalize your letters. Don't put a space between the name and the parentheses. Do capitalize the Roman numerals. Finally, do not apply the Roman numerals when you don't need to. So do not do calcium 2. Do not do sodium 1. Do not do aluminum 3. Just write sodium, aluminum, and calcium for those. Okay? Be careful. Make sure that you are following these guidelines. Oh, you know what I need to do? I need to actually write out all the Roman numerals in case you don't know them. So If you don't know the Roman numerals, here they are. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. We only use Roman numerals in 3 things in this world. The first is the Super Bowl. The second is numbering Final Fantasy games. And then the third one is naming metals with variable charges. So a very unlikely alliance between the NFL, Square Enix, and chemists, but there you go. All right. That's how we name the metal part. Naming the non-metal part is pretty trivial because you have seen most of these before and probably can already put the "-ide" in the correct spot. But just in case you haven't seen those, I don't have a list of... Do I have that table? No, I don't. Okay. There is a table in your book, but I will write them out for you right here. All right. So for elements in group 17, we change the ends just to "-ide" like this. So instead of fluorine, it's fluoride, chloride, bromide, and then iodide. For group 16, we've got oxide, we've got sulfide. You might see selenide, we'll just put it on there. You're probably not going to see telluride, so we won't bother with that. Nitride and phosphide. And I'll put arsenide up there, but it's not very common either. All right. Now, interestingly enough, this is not one of them. We're not going to see carbide because you might think, oh, well, carbide is an ion. It's just this, right? Well, it turns out it's totally not. Carbide is a polyatomic ion. So we're not going to see that. Don't worry about this. Pretend it didn't exist. So there's our ides. Now you'll notice that up at the top it says the ide name is used for ions only. So be very careful that you are not accidentally calling something with ide when it shouldn't be. So for example, this is fluorine, but this is fluoride. This is what's in your toothpaste. This will kill you. The difference is 1 electron, but it's a big difference. Yeah, so something that is carbide does have the carbide polyatomic ion in it, but it doesn't follow this pattern. So I know that people have heard of carbide, so just be aware that that's a thing that comes up. All right, so now we can put all of this information together. You're going to name the metal and name the nonmetal. So how do you name this? Well, I go look on the periodic table. K is potassium. Br is bromine, which we'll call bromide. Potassium bromide. There you go. All right, how do I name this one? The first element is a metal. It's sodium. The second element is oxygen. That's oxide in an ionic compound. Sodium oxide. There you go. Now notice that even though I have a 2 here, I only write the word sodium. We have not said anything about numbering the number of elements or atoms in a compound. Don't worry about it. Do not add any number prefixes in ionic compounds. Just name the metal, name the nonmetal with ide. That's all you do. If I give you transition metals, in order for you to practice your naming with them, I have to give you information about them because you have to be able to determine what the charge is. So for instance, this is cobalt 2. And this is chloride. So the name would be cobalt 2 chloride. What would its formula be? Well, we could just stick the ions together and balance them out so that they have a net charge of 0. And there you go. How about this one? I'll give you a second to put this together to try and come up with a name. You type it in the chat if you'd like. Then we are going to turn you loose on the examples, and then we'll take a break. So for this ion, if we look it up on the periodic table, it's manganese, and its charge is 2, so I wrote manganese 2. And then this is oxide, and that's the name. As for the formula, the charges already balance out, so I can just put them together. And I get MnO, PQRSTUV, WXYZ. All right, so you've seen some very basic examples. So what I want you to do is I want you to name these compounds. You'll notice there's no transition metals on the slide because they're on the next slide here. So I'll have you do these. I'm going to give you about 4 minutes to do that. Put all the names in the chat when you get them. Then I'll put the second set on the board, and you can do those, and then we'll take a break. All right, one more minute. We'll go over the answers. All right, let's go over the answers here. So the first element is lithium. The second is oxygen, which becomes oxide. So this is lithium oxide. We got beryllium, and then we've got chlorine, which becomes chloride. Aluminum, and then oxide. And then potassium. Wow, I skipped all sorts of letters there. And then I is iodine. It becomes iodide. Now, working backwards is a little bit more involved because this just tells us what the ions are. We have to actually put the ions together. And you can do that by remembering we got to balance out the charges so that we have the same number of positive and the same number of negative together. So that would be strontium bromide. For rubidium nitride, here's rubidium. Here's nitride. How do we get these ions? Remember, we want to write out the configuration of the element and then make it match a noble gas. We want it to have a full S&P subshell. Sodium sulfide down here. Sorry, cat. There's sodium, there's sulfide, so this becomes Na2S. And then finally, magnesium and iodide, Mgi2. And if you need me to work out how I balanced the charges on those, I can. I can draw the little diagram up here for you. Just let me know. But we are due for a break here because I believe it is almost 1. So, yeah. So, I'm going to put the second slide on the board here just real quick. Give you a sec to hit print screen or something. And then we'll go take a break. So I'm going to put the break card screen up real quick. I'm going to squirt bottle the cat again. And I'll see you in 10 minutes. Let me get the music up here. Alright, we're back. I'm going to leave these on the board here. Go ahead and give the names for these, and then we'll go over the answers in a little bit. I'll give you like 4 or 5 minutes to do it. One more minute, we'll go over the answers. All right, let's look at these. So we've got cobalt with a +3 charge. Cobalt 3. We got Br-, which is bromide. There's the name. And the formula would be, well, if there's 3+, I need 3 of these negatives to balance it out. There you go. For this one, I have titanium with a 4+ charge. So titanium, parentheses 4, oxide. And to balance this out, these come in -2s, and I need 2 total to get to 4+, so TiO2. And then I have chromium 2. And then S is sulfide as an ion. And then they're both have a 2 charge, so I just need one of each of them to get CRS. What a terrible night to have a curse, right? Chromium 2 sulfide. All right. For these, you could just write the ions out. And so that should be pretty trivial to do. And then for that, that's PT4+, and then fluoride. And you can make those into formulas if you'd like. All right. Let's move on. The next section is just more or less of the same of this. It's just that we're going to include polyatomic ions in here. If you see a polyatomic ion in your compound, all you do is drop the name into the box. You don't modify it in any way. You don't add "-ide". You just overwrite the box with the polyatomic ion. Now, all the polyatomic ions are at the start of Chapter 6. Remember way long ago when we were doing Chapter 6, like week 3 or 4 or something like that? Yeah. I'm sure that you forgot all about the polyatomic ions. You do need them now, so you'll have to refer back to those if you have not memorized them. And yeah, it's an online class, so you didn't memorize them. It's fine. It's fine. Insert image of dog drinking coffee and burning fire. It's fine. But you do need to have those available to be able to name polyatomic ionic compounds, because they're going to pop up on the quiz, they're going to pop up on the exam, and you'll need to know how to name them. So here's how we do that. So first we name the thing that we know, and then we would look for what the thing is that we don't know. That's on our chart somewhere on a polyatomic ion list, and it turns out that the name of this is permanganate. So this would be potassium permanganate. Something I do want to point out that because I'm writing these as sentences, the first letter I am capitalizing because it's the beginning of a sentence. Do not capitalize the first letter on Canvas. Again, don't capitalize anything. I'm trying to follow the rules of punctuation, and so that's why that's capitalized. What would I name this? Well, I know that this is sodium. So The rest of this must be this with this charge. And so you would need to look up this polyatomic ion to find either bisulfite or hydrogen sulfite. Either of those names is acceptable for that polyatomic ion. If you have a choice, you can use whichever one you prefer. Trying to find my... There we go. All right. So I have more polyatomic ionic compounds here for you to name. This does require you to look things up, so I'm going to give you about 3 or 4 minutes to try these, and then we'll just go over the answers so that you have them handy. Okay? Back in a bit. One more minute, we'll go over the answers. All right, so these really just come down to recognizing what they are, which isn't so hard to do, and then finding them in the chart and then writing their names, which is more tedious to do. So the first one has ammonium, and it has sulfate in it. Oh, excuse me. Then we've got potassium, and everything else is chlorate. We've got barium carbonate. Where's the chart with the names? Beginning of chapter 6 slides. So go to the modules tab, open up the slides for chapter 6. One of the first 2 slides or so has all the charts on there. And then we got lithium and dichromate. And then working in reverse, here's sodium, here's hydrogen carbonate or bicarbonate. There's the formula. Here's ammonium, here's nitrite. And then we've got potassium and phosphate. There you go. That's polyatomic ionic. I've got some more of these. I'm just going to write the answers on the board here because I don't have enough time to do them. Oh, that's wrong. Hold on. So there's those answers if you'd like to go over those on your own time. I really want to get to or get through the naming today if I can. When you have multiple groups, make sure you are putting parentheses in the right spots. Otherwise, you end up with really weird looking numbers. Do not try and merge the numbers. That is, don't multiply the 2 through and write Cl2O6. That is not the same thing. So whenever you are involving polyatomic ions, keep the polyatomic ions together as they are presented on that chart. Don't do any distribution of numbers. So for instance, if I wrote the formula for this compound, calcium with a 2+ charge and hydroxide, I would not write CaO2H2. I would write Ca parentheses OH close parentheses 2. Like that. So preserve the polyatomic ion. Obviously, the charges go away because there can't be any charges in a ionic compound. But you do want to keep the OH there so we recognize, oh, that's hydroxide. All right. I'm going to leave those exercises for you to do, just as an exercise for balancing out charges. we're going to move on to covalent compounds. For ionic compounds, we had a naming scheme that we just went over. Name the metal, name the nonmetal with "ide." Draw a big line on your paper or go to the next page or do something to note that this is a different naming scheme, because you'll notice that now we have these hashtags in front of our words that we're going to be writing down. They're connected, which means that they are prefixes in front of the word. So this number is a prefix. We're going to name the first element in the compound. And then we're going to name the second element with "ide," just like before. We're going to attach the numeric prefix in front of it that counts how many things there are. So if there's 1, we would write mono, and there's 2, we would write di, and so on and so forth. Now, how do you know what element goes first in these compounds? Because if they're not metals, they're both nonmetals, how do I know which one to put first? The first element is the one that has the lower electronegativity. It's more positive, so we're going to put it first. The one that has the higher electronegativity goes second. So that's why these substances have been ordered how they have. Now, this is almost always true. There are some weird conventions that are done with certain specific issues that H crops up in, particularly acids versus bases. So H is kind of the exception. We just put in an H in a specific spot. But for the other elements, we follow this pattern. Less electronegative goes first, more electronegative goes second. Now, we only use these numeric prefixes for covalent compounds. Just like we only use Roman numerals for ionic compounds, for our metals, we only use numeric prefixes when we're doing covalent compounds. How do you tell if something is covalent? You check the difference in electronegativity between the 2 atoms that are involved if it's a binary ionic compound or a binary covalent compound. Or you could just look for metals and only nonmetals. If you see any metals, it's ionic. Use the Ionic rules. That'll be good enough for us. On the screen are the numeric prefixes. Mono, di, tri, tetra, penta, and then from then on it's just shapes. Hexa, hepta, octa, nona, deca. We have some extra exception rules that are applied here when naming. The most common one is that whenever you have one of the first atom, you don't write mono. So for CO2, for example, you do not write monocarbon dioxide. The mono is implied for the first element. You do not need to write it if there's only one. So for CO2, I would write carbon dioxide. For CO, I would write carbon monoxide. And that makes sense, except it sounds a little weird, right? Well, if you have mono and you end up with a double O, or you have some prefix that ends in A, which is most of them, and the next letter is O for oxygen, we get rid of the last letter of the prefix. So for anything that has oxide in there, you may chop off the last letter of your prefix. So hexa would become hex, or tetra would become tetra. Tetra. Instead of saying tetraoxide, you'd say tetroxide. So some examples down below. P2O5 diphosphorus, because there are 2 phosphoruses involved. Pentoxide instead of pentaoxide. We drop the A to make it sound better. For CO, we go carbon monoxide instead of carbon monoxide. Or carbon monoxide. We don't need to have that many O's in a row. Carbon monoxide. Yeah, exactly, right? All right. No Roman numerals in molecular compounds. That is for metals. In ionic compounds only. Now, what would I call this? Using these nomenclature rules, This is nitrogen. There are 2 of them, so we'll append the prefix di in front. This is oxygen, which we'll name oxide. There are 5 of them. We'll apply the prefix penta. And then drop the A because it's an oxide. How about this? This is sulfur. I don't have to put monosulfur because there's only one, and it's the first element. This is oxide. With 2 of them, I call it dioxide. Easy enough, right? What do I call this? Hint, you can't call it water anymore. I mean, you can. You just can't type that in for its name. Well, okay. We got hydrogen. Now we've got monoxide there. So that would be the name of that one. And this brings up a fun segue that I like to call the petition to ban dihydrogen monoxide. You may have heard of this. This is a real thing that somebody did as a practical joke and got lots and lots of people in a panic. We'll talk about this in a second. Actually, I guess we'll start with this. So, the whole point of nomenclature is to make a systematic set of rules so that you can name anything that you come across, and that you don't have to memorize a bunch of names. You're memorizing a system instead. However, one consequence of that is that the names sound very esoteric if you don't know the jargon. And so, as non-chemists, before this class, you may have been intimidated by chemically sounding names. Now, here are 2 scenarios where people realized that and then decided to either to take advantage of it in some way, we'll say. So scenario 1 and scenario 2. I'm going to describe them. One of these happened in America. I'm going to let you try and guess which one. So scenario 1. The Senate / Parliament / House of Representatives / whatever the governing body is of this country in question. They passed a bill banning dihydrogen monoxide, stating all of these reasons that you're about to see. And a lot of people were like, oh my goodness, this is so terrible. And then when the bill actually did pass, this was actually on April Fool's Day that this happened, they all laughed and then made a message to the public that was like, hey, we did this for a reason, to highlight chemical awareness and education and why it's important to, like, not be scared of this. So they did it for, like, a positive outlook sort of thing. Case number 2, a radio station on the air mentioned the presence of dihydrogen monoxide in everybody's drinking water. And then they listed all of these effects that you're about to see on the screen. Within an hour, so many people had called in this radio station in a mass panic that they had shut it down. And the radio station hosts were banned for like a week and a half. Apparently, the state that this happened in, or country, or whatever, it's a felony to pretend that water treatment is... To falsify water treatment status or something like that. Yeah, number 2 is totally us. This happened in Florida. Of course it did, right? Florida or Georgia. You can look this up. Look up dihydrogen monoxide radio, and you can read the article about it. Here are some of the things that were on the article. What is dihydrogen monoxide? Oh, well, there are many names for it. One such name is hydroxyl acid, and it is the major component of acid rain. That's pretty sketch. I don't know about you, but major component of acid rain? Yeah. Contributes to the greenhouse effect. In fact, this is a much more potent greenhouse gas than CO2. Everybody's worried about CO2, but DHMO, like hundreds of times more effective at holding heat. Maybe we should turn our concerns elsewhere, you guys. It is possible that contact with this can cause severe burns, and if you breathe it, you will die. It's all over the natural landscape, and it causes erosion over time. Like, who knows how long your yard will last, like nature will last. DHMO will eventually eat it all away. It accelerates corrosion and rusting. It's prevalent in everywhere, and it just accelerates rusting. You get this on your metal, and it's going to turn into rust. It screws with electrical circuits. It wrecks your brakes. Every single person who has died of cancer this has been found in their bodies. Like, this is serious, you guys. This is really bad. And yet, despite all these problems, dihydrogen monoxide is still used in these ways. We still use it in industry as an industrial solvent and coolant. We use it to make styrofoam. We use it in nuclear power. We use it as a fire retardant. We use it in animal research. It's everywhere. We even use it to distribute pesticide. All of our produce is contaminated, and if you wash your produce, you can't get rid of it. It's still there. It's used in junk food. It's everywhere. It's in all of our food, and it's everything we drink and everything we breathe. And you know what? It's fucking water. For fuck's sake. It's fucking water. Right? So, yeah, all of these things that I listed, they're all water. Of course, if you breathe water, you will die. You drown, right? Of course, it can burn you. Anything can burn you if it's hot enough, right? So, be very careful about anything that involves chemical nomenclature, because the whole point of some organizations is to try and pull the wool over your eyes by sounding off like really, really dangerous sounding things. For instance, this is a website that exists. This is dhmo.org. And I don't know if I can actually get the search bar on here. Can I get this to show up? Kind of. There we go. What we're going to do, you can see my taskbar here and everything here. So if I type in water, you'll notice that there are 0 hits on dhmo.org for all of this information about DHMO. The word water does not appear once. Now, I believe that this is meant to be a joke. However, given the scientific literacy levels of Americans, I'm not so sure. So, whenever it comes to chemically sounding stuff, do the research, look up what it really is, and be careful. This is another one of those, just language moments where you don't want to embarrass yourself. A long time ago, there was a television show called The Man Show, and it was basically like, I don't know, chauvinism taken to an extreme, I guess, so that it was funny. And one of the things that they did on the show is somebody had a petition to end women's suffrage. And thousands of women signed it, saying, I don't want women to suffer. Thousands of men signed it too for the same reason, probably. What is suffrage? It's your ability to vote. So don't be a dumbass. Know what it is that you're talking about before engaging with people that are going to try and manipulate you for your lack of knowledge. All right. On the screen are some molecular compounds. Please name them. At the bottom, I have the names. You got to be able to turn it into a formula, so you got to go in both directions. We'll go over the answers in a few minutes once the cat goes away. The cat is starting to like getting sprayed with the water bottle, and I'm concerned about this now. All right, one more minute. We'll go over the answers. All right, let's go over the answers here. All right, so we've got dinitrogen monoxide. I like that nobody's putting any answers in the chat. You're just talking about HCLing my pets. No. I looked at my cat and said HCL, and he did run away, so do not HCL the cat. So we got dichlorine. Be careful with that. Don't put dichloride because chlorine is the first element. Trioxide. Then we got SF6, which is sulfur. Hexafluoride. And then P4, tetraphosphorus. And then 10 is decoxide. There you go. And then turning formulas into molecular compounds is pretty easy. So B2O3 for boron trioxide, carbon disulfide, oxygen difluoride. And there you go. Sulfur hexafluoride is the deep voice gas, yeah. You could do this with xenon and maybe to some extent argon. Or krypton, yeah. Because sulfur hexafluoride is totally inert, and its density and molar mass are way higher than the average of air, if you breathe it, your vocal cords vibrate much, much more slowly, and the frequency of your voice goes like this. I can't really go that low. I can do the high end, though. This is what happens when you have helium. That actually hurts me, so I won't do that anymore. But there are all sorts of gases out there that you can do that with that are inert. You just have to make sure you don't asphyxiate yourself by running out of oxygen, which would be bad. When we come back next week, we are going to name all the acids, and then we're going to start drawing Lewis structures forever, because that's going to be what we do for the remainder of the class. So join us again for Monday next week, where we will continue Chapter 4. Do mind that quiz number 3, I should call it quiz Chapter 3, and lab worksheet number 4 are both due on the same day. You really don't want to hit Wednesday night where those are both going to close and you got to turn them both in. So work on that quiz over the weekend. Work on the lab over the weekend. Talk to people in the chat in the Discord channel, or send me email questions so I can help. Oops, I don't have this open. How will I do the outro if I don't have the outro music? Okay, there it is. All is well. Thanks for coming to the lecture. I will see you on Monday. Or no, Tuesday next week. Take care.